ratio, fractions. So when we say fractional exponents, we're talking about something like this, and it's very important to remember that relationship. It's a very important relationship. It comes up a lot in this class. When you have a fraction for an exponent, the denominator of that fraction is the root of the radical, and the numerator is the power on the what we call the radicand underneath the radical sign. Now this can also be written as n through to a to the n. Those are all equivalent statements. Sometimes it's easier to look at it this way, sometimes it's easier to look at it this way. But that's a very important property that you need to be aware of in an algebra class. So let's look at one of these. Number 36 on page 178. All right, so we got 8x to the 5/3 minus 24 equals 0. So 5/3 minus 24. Okay, so notice here we have a fractional exponent. So what we're going to do here is we want to isolate that term with the x, and we want to isolate this term. Have that on one side and everything else on the other side. So whatever the term is that has the fractional exponent in it, that's what you want to isolate. So first we're going to add 24 to both sides. And then we're going to divide both sides by 8. All right, 24 divided by 8 is 3. And now we're at a point very similar to the square root property, except it's not a square. Right? If it was x squared equals 3, we would take the square root of both sides because we want x to the first on the left-hand side. So now we got x to the 5/3. So what we got to do is say, what do we need to raise that to get x to the first? Well, just the reciprocal of whatever that fraction is, right? Because remember this rule says when we raise something to an exponent to a second exponent, we multiply those exponents together. So we got to say, what do we multiply 5/3 by to get x to the first? Well, just the reciprocal. Right? We multiply 5/3 times 3/5. I'm going to get x to the first. Well, whatever I do to one side, I have to do to the other side, right? So this also has to be raised to the 3/5. All right, so now this just becomes x to the first, which is what we're looking for. And this, coming back to here, this is 3 to the 3/5, or the 5th root of 3 cubed. Now if you just leave it like this, you'll probably get maybe a little bit taken off. I'd like you to finish and see if it simplifies. So you look at it, again, either way. You look at it this way and see if it's easy to look at. If it's not easy to figure out here, look at it this way, see if it's a little easier. 3 cubed is what, 9? 27. So the 5th root of 27, that's nothing really to, if it was 32 or something, the 5th root of 32 is 2. But this is not something easy. So any of these would be acceptable as answers here. If you can simplify the fractional exponent and get a number, and it's always good to check. But if you get this far, you've done good work. All right, so we isolate the term with the fractional exponent in it. Then we raise that side to the reciprocal of the fraction to get x to the first. And then we manipulate the other side to get our answer. All right, one last thing here. Actually, a couple. Let's look at number 42 on page 179. And this is an example of an equation that is quadratic in form, which means it's not exactly like the ones we looked at earlier, but it can be changed so that we can look at it that way. So we said number 42, x to the 4th minus 13x squared plus 36 equals 0. All right, so this is not a quadratic, right? Since the highest exponent is 4, we can't use the we can't use the quadratic formula here. But we can look at this and make a u substitution and create a quadratic equation. Okay, that's what we're doing here. So notice we got an exponent of 4 and we got an exponent of 2. If I create another variable, let's say u, and let u equal x squared. All right, so then u will go here, and u squared will go here, right? Because x squared raised to the second is x to the fourth, which is what we want here. So we change this. If we let this happen, now we get a quadratic. U squared minus 13u. Nothing changes over here, and we get the 36. Right? Now there's no x or u in this term, so that doesn't change. Well, now hopefully we know how to deal with this, right? The only thing here is you got to remember and go back and solve for x. We're going to solve this and get u values. And we want to go back here and solve for x. Okay, so here, we use again any of the methods that we discussed. And it looks like a zero factor property is generally the first thing you want to check. Quadratic formula will always work when it's in this form, but it's a little bit more intensive work. If you can factor it, that's always the easiest choice. If you look at 36 and you think about 9 times 4, you can get a 13 out of 9 and 4. So that's what we want to do here. Factor this into 9 and 4, and then look at the signs. We want the sum to be negative 13, but the product to be positive. So we got to put negatives on both of those values. And easy to check, right? Use the FOIL method. Make sure you come back with this, which you will. So now we're going to get to u values. When does u minus 4 equal 0? When u equals 4. When does u minus 9 equal 0? When u equals 9. Okay, now we're not solving for u though, we're solving for x. Well, we know this is true, right? So now all we got to do is take those u's, put that 4 into here, solve for x, put that 9 into here, and solve for x. And again, notice, highest exponent is 4. We're going to end up with 4 solutions. So now we'll come over here and say if u is 4, then 4 equals x squared, and this is the square root property. Right here, we take the square root of both sides, and we get plus and minus 2. 2 answers, and if u is 9, then 9 equals x squared, and plus and minus 3 equal x. So we get 4 answers, right? Plus and minus 2, plus and minus 3. 4 answers. 4 was the highest exponent on the equation. All right, so that's a way to take a higher degree. The highest number is, the highest exponent is sometimes called the degree. Highest degree, higher degree polynomial. Sometimes you can use a u substitution. It doesn't have to be u, it can be any letter you like. You make a substitution to create a quadratic equation, quadratic in form, or we say quadratic in form. Solve that quadratic, and then make sure you come and finish the problem to get the x's. All right, one more thing in this section is absolute values. An absolute value of x, you're going to see this is the symbol for absolute value of x. And absolute value is, if you were to graph it, it looks like this. So basically it's the distance from 0 on a number line. So if the number inside the two brackets is positive, then the absolute value of that number is just that number. So like over here, if we say 3, the absolute value is 3. If it's negative, if this number in between the brackets is a negative value, we take the negative of that negative value, right, to get the absolute value. So over here at negative, we're talking about if the value within the brackets is negative, if it's less than 0, we take the negative of a negative. So negative 3, we also get a positive 3 for the absolute value. Right? So it's always above the x-axis, it's always going to be positive or non-negative. Right? It can be 0, absolute value of 0 is 0, but it's always going to be non-negative. So when we solve absolute value equations, we have to deal with that fact. So let's look at an equation involving absolute values. So number 64 on page 179. So number 64, we have the absolute value of 2x minus 3 equaling, sorry, 64? No, x plus 1, sorry. X plus 1 equals 5. All right, so this is an absolute value equation. So what we have to realize here is we need what's inside the absolute value brackets. If what's inside here equals 5, then it's a true statement. But if what's in here equals negative 5, it's also a true statement. Okay, so you got to break this up into two parts. Whenever you have an absolute value equation, first you want to isolate the term that is the absolute value. Here there's nothing out in front, there's no denominators, it's already by itself. So this one is already set up for us. So you want to get to this point first. This one's already here. So now once you get here, you're going to say this is true if x plus 1 equals 5, or if x plus 1 equals negative 5. Okay, so we're going to say this is true if x plus 1 equals 5, or if x plus 1 equals negative 5. So you got to do both of those. Again, very simple equations here, right? We subtract 1 from both sides here, we get one of our answers. We subtract 1 from both sides here, we get our other answer. Again, always good to check. You put 4 in here, you're going to get absolute value of 5 equals 5, which is true. If you put negative 6 in here for x, you get negative 6 plus 1, which gives you a negative 5. Absolute value of negative 5 is also 5, so we get 2 answers. Okay, so that's how you deal with absolute values. Now one more thing, and we'll be done with chapter 1. Number 105 on page 105. Let's see here. I want to do one where let's see if I can choose one here. Okay, let's try number 68, just to show an absolute value equation that's a little bit more difficult than the one we just did, but not really too much more difficult. The only difference is on this one, as you can see, we have another number on the left-hand side, whereas here we didn't have anything but the absolute value. Here, we want to isolate the absolute value first. Again, you probably see this isn't really too tough. We just have absolute value of 2x minus 1. We divide both sides by 3, and now we're right back to where we were. We say this is true if 2x minus 1 equals 7, or if 2x minus 1 equals negative 7. We solve both of those. We get x equals 4, or x equals negative 3. We check that. 8 minus 1 is 7. 3 times 7 is 21. Put negative 3 in there, we get 3 times 7 is 21. They both